Today is the last day of trigonometry, and we're going to work with triangles that law of sines could not work with. So with law of sines, if you remember, we could use angle, angle, side, angle, side, angle, side, side, angle, although we had some ambiguity there. Today we can work with triangles now where we're given 3 sides to get the missing angles, and we can also work with triangles where we're given 2 sides and the included angle to solve for missing angles. So first and foremost, let's go ahead and look at the 2 triangles that we're given, the one shaded in yellow and the one shaded in pink, and derive the law of cosines. So in this yellow triangle, I'd like to first use cosine because it is the law of cosines, and we're going to use reference angle A, and cosine is adjacent over hypotenuse, so we're going to set that equal to x over c, multiply both sides by c, and we get x equals c times cosine A. I do want to set up another equation with this yellow triangle, and I'd like to use the Pythagorean theorem. So leg squared plus leg squared equals hypotenuse squared. And then I'd like to solve for h squared by subtracting x squared from both sides. And we got h squared equals c squared minus x squared. If that feels all right, the last thing that we're going to do is use the Pythagorean theorem now on this pink triangle. So that's leg squared plus b minus x squared equals a squared. A couple notes here. The base b was split into x and then b minus x. And then also we need to put b minus x in parentheses to make sure we're squaring that whole term. And if you recall, b minus x in parentheses squared is b minus x times b minus x. So you'll have to use foiling, for example, or double distribution. So if I want to simplify this a little bit further, and I'm going to go ahead and bring this down because I know I'll run out of room, I have h squared equals, and I'm sorry, by equals I mean I have h squared plus b times b, the first terms. If I do the inside terms, I get negative xb or bx, and I get negative bx, so that's going to be negative 2bx. And then x times x, as the last terms, is going to be plus x squared, and then equals a squared. And now I'd like to do some substitution. So for the h squared, I'd like to plug in the c squared minus x squared. So the only thing I'm going to change first is substituting in that expression. Everything else stays the same. And then the other term I'd like to replace or substitute in term, it's really a variable. I'd like to substitute in c cosine A for x. And so that becomes c squared, oopsies, that becomes c squared minus x squared plus b squared minus 2b, and then instead of x, we're going to substitute in c cosine A plus x squared equals a squared. And from here, it's simplifying to finally get that law of cosines. So if you take a look, we have a negative x squared and a positive x squared. Those cancel out. And then what I'd like to do to write this final version of the law of cosines is manipulate the equation a little bit. So instead of saying that it's equal to a squared at the end, I'm going to do a squared equals. And then we can change the order that we add numbers and we get the same sum. So I'm going to put the b squared first and then plus c squared. And then the last part is to subtract the 2bc cosine A. So you may be asking, what does this look like in terms of the general law of cosines? And so let's go ahead and summarize the 3 different cases, and I'll go ahead and try to color code to help with this. So we have the basic version that we just wrote above, a squared equals b squared plus c squared minus 2bc cosine A. We have b squared equals a squared plus c squared minus 2ac cosine A. And last but not least, we have c squared could equal a squared plus b squared minus 2ab cosine c. What you should notice here is that the side that is squared and set equal to everything else is going to be the side opposite the angle we're taking the cosine of. You should notice that the first term we are squaring is also going to be multiplied by 2, and the other term that we are squaring. And so there definitely are commonalities. We're going to go ahead and take a look at 2 examples of applying the law of cosines so you can see it in action. So in this first example, we have a side angle side case where we are given 2 sides and the included angle, and we can go ahead and jump right into the law of cosines. So if you notice, we are given angle B, we are given side A, and we're given side C. And so I'm going to solve for b by using the general form b squared equals a squared plus c squared minus 2 times those sides times the cosine of b. And from here it's a plug and chug. So I have a squared is 25 squared plus c squared is 12 squared minus 2 times 25 times 12 times the cosine of 80 degrees. I want you to just plug this into your calculator, and once you get what b squared is equal to, go ahead and take the square root of whatever number that is, and you will get b is approximately 25.78 centimeters. And we have solved for the missing side. So then what comes into play is solving for the angles. We need angle A and we need angle C. And we are going to use the law of sines to solve for these two angles. Really, we can solve for one using the law of sines and then take away angle A, for example, and angle B from 180 to get the measure of angle C. One of the things that we do need to note with the side angle side case in particular is that you want to solve for the smallest angle first. I am going to reference what we've seen before when we established the law of sines. And if you recall, on a coordinate plane, if I have a fixed segment, the hypotenuse, and I rotate it a given angle, for example, 20 degrees, and if I want to form a right triangle, I would drop down a perpendicular segment to the horizontal. And I hope you can agree that this would be the opposite side from 20 degrees, and then the bolded segment would be my hypotenuse. Now, if you recall, if I go the supplement of 120, which is 160, so I've just traveled this hypotenuse 160 degrees counterclockwise, and let's say I want to form a right triangle, I still drop down that segment perpendicular to the horizontal, and I really hope you guys can see that this opposite is going to correspond to this opposite. Like that distance to the horizontal did not change, and then clearly the hypotenuse didn't change because that's the segment I was rotating to begin. And so whether I take the sine of 20 degrees, which formed the triangle in the first quadrant, which was the opposite over hypotenuse, or I take the sine of 160, I still get the same ratio of opposite over hypotenuse with the same measurements. They're both positive. And so that's when we concluded that the sine of an angle is equal to the sine of its supplement. The reason I bring this up, if I wanted to take, the arc sine, for example, of a ratio, I wouldn't know if I'm getting 20 degrees as my answer or an angle is the supplement, like a 160 degree angle, unless I guarantee I work with the smallest angle of the sides that I have and I work for the smaller angle. So when I highlighted that green part and I say solve for the smallest angle first, that means that we don't have to worry when I get this degree of 20, is it really a 20 degree angle or is it the supplement, the 160? Because we will be solving for the shortest side, we will be solving for the shortest angle. And so from here, I'm just going to go ahead and set up. You would use that base ratio of the 80 degree for angle B over the side we just calculated, 25.78, and set it equal to, and actually in this case, I'm just noticing in the diagram, C is the smaller side, so we want to set up the C law of sines ratio. So I'm going to change this to sine of 80 over 25.78 equals sine of C over the C measurement side is 12. From here, you would do some solving. You would set up arc sine of 12 sine 80 over 25.78 to calculate C. And from there, you get C is about 27.28 degrees. And I don't have to worry, okay, is it 27.28 degrees for this angle or is it the supplement, which is like 153? Because I solved for the smallest side, I know it cannot be an obtuse angle. So C has to be 27.28 degrees. And then the last piece would be, next the law of sines, we could take the 180 minus B minus C to get A. This last example is one using side, side, side. So given three sides in a triangle, can I determine the missing angles? And so this, I'm bringing this diagram back and it's pre-drawn for you. We just discussed that the sine of an angle is going to create the same triangle as taking the sine of a supplement. However, when we look at cosine, we are not looking at opposite over hypotenuse. We are looking at the adjacent. And so if we look at this as a coordinate plane, and when we write the ratios for cosine, the cosine in the first quadrant, so first quad, would be positive. Cosine of theta, whatever that might be, is going to be a positive over a positive. The adjacent is positive, the hypotenuse has to be positive. If, however, we rotate that segment, the hypotenuse, into the second quadrant using the supplement of theta, I am going to get that the adjacent side here is negative. And so cosine of any angle, 180 minus theta, for example, in the second quadrant is going to be negative over positive, meaning that if you go past the 90 degree mark in your coordinate plane, then you have an obtuse angle, and again, that ratio is going to be negative. The whole point being, here we need to establish if we have any obtuse angles first. And so, to figure out if we have any obtuse angles, we're going to go ahead and use the biggest side because the biggest side is opposite the biggest angle. And so when we set up the law of sines, we are going to use b squared equals and solve for the missing angle b to error out any obtuse angles and then only concern ourselves with the law of sines and acute angles for the same reasons that are on the previous page. If that explanation doesn't work for you, I'd encourage you to please read the read the print and the paragraph to see if that can make better sense to you. Right now I'm going to go ahead and apply what I just discussed. So b squared equals a squared plus b squared. And by b squared I mean c squared. Minus 2ac cosine of b. So here I have 25 squared equals 15 squared plus 12 squared minus 2 times 15 times 12 times cosine of an unknown angle that we will eliminate as an obtuse angle as soon as we solve. So 625 equals, if I add 15 squared and 12 squared, 369 minus 360 cosine b. Here, you cannot combine. These are not like terms. The 360 is a coefficient on cosine b, so you will subtract 369 from both sides, and I believe you get 256 equals negative 360 times cosine b. To isolate the b completely, you'll divide both sides by negative 360, and we get cosine of b equals 256 over negative 360. And if you recall from here, we could go ahead and take the arc cosine, inverse cosine of the negative 256 over 360 to calculate b. And this way we get b to be approximately 135.33 degrees. From here we would use the law of sines to calculate a, so we could do sine of angle a over its opposite side, 15, and set it equal to sine of the 135 degree angle over 25. And then solve for c by taking away both angles from 180. Again, here it doesn't matter which side I use to solve for which angle first because I know that the other two angles have to be acute now that I've established my obtuse angle. And if I could bring it back even one step further before closing out these notes, if you noticed in solving that equation for the cosine of b and ultimately angle b, there was a negative ratio here. Well, that should ring a bell from that little description above of if you have a negative ratio, that means that you pushed into the second quadrant to get that negative adjacent side. And so that means that you have an obtuse angle and you should anticipate that before taking the inverse cosine of both sides.